Okay, sample exam here for exam number 2 for Chem 151. So moving on to the second problem on the exam here. We are presented with a syringe containing 1.55 milliliters of oxygen gas, and this syringe is cooled from 95.3 degrees C to 0 degrees C. And we're asked to find the final volume of oxygen in the gas. So we're given a volume, right, and we're asked to find the second volume, and we're given two temperatures, so the initial temperature and a second temperature. So this, I would describe this as a change of circumstances problem, right, which means PV equals nRT, or the ideal gas law, is not going to be the appropriate way to approach this problem, but it's good to use PV equals nRT to help analyze what would be the right equation for this problem. And the way that I like to think about doing that is to move all the variables that are changing over the course of the problem to one side and put the variables that aren't changing on the other side. In this case, since V and T are changing, but the pressure isn't mentioned, so the pressure stays the same here between the circumstances. The number of moles of gas stays the same because it's one oxygen sample, and R always stays the same. What we want to do is put V and T on one side of the equation, P, N, and R on the other side. So from PV equals nRT, I'll divide both sides by T and divide both sides by P, and I'll end up with that equation. V over T is equal to NR over P. Now we know N, R, and P in this circumstance are all constants, so that means V over T is equal to a constant. And that means V1 over T1, the initial circumstances, is equal to the same constant as the ratio of V2 to T2 would be, right? And within that analysis is the formula we want for this type of problem, and it would be that formula. V1 over T1 is equal to V2 over T2. Since we're solving for V2 here, we could rearrange, multiply both sides by T2, and we would end up with T2 times V1 over T1 is equal to V2. And from there, we want to plug in those variables. Now, there is another caveat, particularly for this question, and really for any gas law question. If you're doing a gas law problem, those temperatures are always absolute temperatures. They are temperatures in the Kelvin scale. So we do want to change both of these temperatures to Kelvin. Now, in this case, you should probably be a little bothered by the 0 in there, because if you plugged 0 in here, that would give you 0 volume, right? Did your gas have 0 volume? No, not until it gets to absolute 0 anyway. At least for an ideal gas, it would still be a gas down to 0. So to change both of these to Kelvin, we need to add 273. So our second temperature would be 273 Kelvin. And it does go to the tens place, so it would be 273.0 actually there. And then 95.3 plus 270, 95.3 plus 273 is 368.3 Kelvin. Okay, and we're just using 273. It's actually 273.15, but generally our temperatures are, if they're significant to the ones place, that is reasonable for the conversion. So T2 is 273, okay. Multiply that by the initial volume, 1.55 milliliters. Right? We didn't use R, so we can keep the volume in milliliters. That'll just be the unit that's left over at the end of the problem. Divide by T1, 368.3 Kelvin. Right? Kelvin's going to cancel out. The unit left over will be milliliters. So 273 times 1.55 divided by 368.3 is, we're limited here to 3 significant figures from our initial volume there, so I'll round this to 3 significant figures as well. So the final volume there of the oxygen sample would be 1.15 milliliters. Now, okay, had a sneeze coming along there. This makes sense, right? Because the temperature went down. So if we're thinking about something like the kinetic molecular theory, right, as the temperature goes down, the individual molecules of the gas are moving more slowly. They have a lower average kinetic energy. Their collisions with the wall of the container will be less frequent and less impactful because they're at lower energy. So it makes sense that the volume of the container may not be as large at that lower temperature. Okay, and with that procedure, you can derive any of the gas laws that you will need for your problem, right? So it's really a function of picking out the data in the problem, using that to figure out, well, how am I going to go about getting the right equation? I've said in class, there's not a lot of benefit from memorizing your equations because you still have to figure out which one to use. So even if you do successfully memorize them, right, you've still got to figure out, this is the right equation for this particular problem. Okay, moving on to number 3. We've got an unbalanced equation first, so we'll have to come back to that and balance that equation. But then we've got kind of a stoichiometry problem. But remember, one of the topics is gas laws. We're going to relate it to gases. Determine how many moles of O2 are required to act with 431 grams of hexane. C6H14 would be hexane, not one you should know at this point. What volume of products would be produced at STP if all 431.6 grams react? Okay, so we're starting with a stoichiometry problem there, trying to get to moles of O2. Then we're going to convert this into a gas law problem. But first, let's try to balance this equation. If we have 6 carbons over here, we should at least try to start out with 6 over here. 14 hydrogens over here, 2 in each water, that would be 7 there. Now from there, that covers carbon and hydrogen. The only thing left is oxygen, so let's see if oxygen works. This would be 12 oxygens from the CO2, another 7 from the water would be 19, but it's got to be an even number. Now 2 and 19, the first place we could balance those two pieces would be the lowest common denominator of 2 and 19, which would be 38. So if I put 19 here, that would be 38 oxygens, and then if I double both of these, that would double the total oxygens here. So 24 from the carbon dioxide plus 14 from the water would be 38. So that balances the oxygen, but I have changed carbon and hydrogen now, so I'll have to adapt to that. If I need 12 carbons, that would mean I need 2 back here in front of C6H14, right? But that would also give me the 28 hydrogens. So 2, 19, 12, 14 to balance that equation. Now, determine how many moles of O2 are required. So if we start with 431.6 grams of C6H14, we can convert that to moles using the periodic table. So 1 mole of C6H14, right? And if I calculate that over here on the side, 6 carbons would be 6 times 12.01, and 14 hydrogens would be 14 times 1.01. So 14.14 plus, that would be 70, better calculator it just to be safe, 72.06. So if we add those together, that would be 86.20. So 1 mole of C6H14 would weigh 86.20 grams, right? That would get us to moles of C6H14. That would allow us to use our equation, right? Determine how many moles of O2 are required is the first question there. So we need 19 moles of O2 for every 2 moles of C6H14 that react. That tells us how many moles of O2 we need. So 431.6 divided by 86.2 times 19 divided by 2, and the answer there is 47. Let's see, I think we have 4 significant figures there, so 47.57 moles of O2 would be required. Okay, so that would be the first part of the problem, just kind of a straightforward stoichiometry problem, sort of out of chapter 3. The second problem, what volume of products would be produced at STP if all 431.6 grams react? So we just calculated if all of the hexane reactant reacts with oxygen, we got this many moles of O2. Now, what we need, though, to figure out volume is to know how many total moles of gas would be present. So all of this oxygen would have reacted as well, but it would have been converted into the products. So if I take my answer from the previous question, 47.57 moles of O2, and then I look to my balanced equation, if all this gets converted to the product, every 19 moles of O2 are going to end up giving me 12 moles of CO2 and 14 moles of water, or a total of 26 moles of gas. So 26 moles of gas will be produced for every 19 moles of O2 that react. And that will tell me how many moles of gas I'd have if this reaction proceeded to the products. And that would be 65.09 moles of gas. Now, because ideal gases all react the same way in terms of their relationship between pressure, volume, and temperature, from the ideal gas equation, we don't have to calculate how much CO2 and how much water vapor there are separately. We can just calculate the total amount of gas. And from there, we can calculate the volume, right? So the other piece of information here is that this is at STP. That stands for standard temperature and pressure. For gases, that means the temp is 273 Kelvin, and the pressure is 0. No, it's not 0, it's 1. 0 degrees Celsius is the temperature, which is 273 K. It's exactly 1 atmosphere, so I'm just going to write it with 3 sig figs. So if I have moles, N, T, and P, I can solve for V. So from PV equals nRT, I rearrange to isolate V. V is equal to nRT over P. 65.09 moles of gas. 0.0821 for R. I'm leaving the units off there for a little bit of speed here because I'm competing against the time of the video. 273 Kelvin, right? And then divide by 1 atmosphere. So I'm putting it in there for units, but dividing by 1 isn't going to change anything. So take my previous answer times 0.0821 times 273, right? And that would give me the volume. So the volume there comes out to be 1,459 liters. Now, we probably do fall back to 3, well, I guess STP, those we could consider exact temperatures, and we could keep this as 4 significant figures from our quantity of moles, right? But that would be our answer to that problem, okay? So we'll stop the video there. We'll pick back up with problem number 4.